Here we're going to talk about work and power, specifically mechanical work. Work has perhaps a bit of a different definition in physics than it does in day-to-day conversation, so we'll find out some specific details on that. In physics, mechanical work done on an object is the total mechanical energy transferred to the object by a force. We can write that using a formula where delta E represents a change in energy for the object. So the work done on an object is equal to the change in energy for that object. Energy transferred to the object or energy transferred away from the object, depending on the type of work, and we'll get to that in a moment. So the mechanical energy of an object is the total energy that it has, which can be changed by mechanical work. Unfortunately, our definition for mechanical energy depends on our understanding or definition for work, and vice versa. Our definition for work depends on our understanding or definition for mechanical energy. So, hence, the Department of Redundancy Department. It's difficult to define work without energy, and it's also difficult to define energy without knowing about work. And energy is a fundamental concept in physics. It's very tough to define energy in terms of anything more fundamental. We use energy a great deal in physics, and in fact, some of the most complicated physics problems can be solved using energy. Problems that otherwise would be extremely difficult to solve. So energy is something that we use a lot, and we can use it very accurately, and it's very convenient for us, but it is very difficult to define in more fundamental terms. It's easier just to understand the types of mechanical energy that we deal with and how we use them, and where we encounter them as well. So we have kinetic energy, and we have potential energies, and there are several different types of potential energies. Kinetic energy is the energy of motion, so any object that's moving has kinetic energy. Potential energy is the energy to potentially do something else. So in other words, potential energy can be thought of as a kind of stored energy, energy that could be changed into some other kind later on to do some work. Here's an example. Thermal energy is the energy of the particles of a substance. It's partly kinetic energy, and it's partly potential energy. The kinetic energy is the kinetic energy of the atoms. The atoms are moving, sometimes vibrating, sometimes moving over greater distances, but as long as they're moving, they have kinetic energy. The potential energy is the energy stored in the formation or deformation of the atomic bonds during this motion, rather. So you can think of this as being similar to objects connected by springs. If you compress a spring, it stores some energy. If you extend or stretch the spring, it stores some energy. And so those bonds are similar in some ways to springs. And we'll talk more about springs and their energy very soon. The units for energy, the standard units or SI units for energy, are joules. Named after this fellow, James Joule. And 1 joule is equivalent to 1 kilogram meters squared per second squared. This should be times, so I'm going to put a little dot there, and that dot means times. So kilograms times meters squared per second squared, but we pronounce it kilogram meters squared per second squared. But there are other metric units for energy, such as the erg. So 1 erg is equivalent to 1 gram centimeters squared per second squared, which is equivalent to 1 times 10 to the minus 7 joules. So that's a very small unit. 1 kilowatt hour, a much larger unit, is equivalent to 3.6 times 10 to the 6 joules, and that's the one that we see on our energy meters. If we're reading our energy bills for the month, we will see the energy in kilowatt hours. 1 calorie is equivalent to 4.184 joules. We'll see calories primarily on food labels. And a calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius at a pressure of 1 atmosphere. Food energy, however, is measured in kilocalories. So when we look at that label, the food label, on something that we buy, some food item that we buy, even though it states the energy in calories, it's actually measured in kilocalories, or calories with a capital C. So 1 calorie with a capital C is equal to 1 times 10 to the 3 calories with a lowercase c. So there's our lowercase c calories. But this 1 calorie with a capital C is really 1 kilocalorie. So 1 calorie with a capital C, or 1 kilocalorie, is equal to 4.184 times 10 to the 3 joules. So, I mentioned earlier that work is done on an object when a force is exerted on it, but there's a bit more to the story than that. The object has to undergo a displacement. And so if the force is exerted on the object and the object moves through some displacement, then work has been done on the object. You'll notice it also says that it's the force applied parallel to that direction, meaning that the force, the direction of the force and the direction of the displacement have to be either in the same direction, or they can be anti-parallel, which means that they're in opposite directions. So anti-parallel would look like this. So F is the magnitude of the applied force, and delta D is the magnitude of the displacement that the object moves through. Work is a scalar quantity, though. So force is a vector, displacement is a vector, but work is a scalar. Let's try an example. Ms. Roseberry applies a horizontal force of magnitude 40.0 newtons to push a 10.0 kilogram box 15.0 meters across a frictionless surface. Find the work done on the box. So we'll write down our given values first, and then we'll write down our unknown value. I guess we don't need a mu. There's our unknown. And now we'll substitute our values and multiply. Now in this case, it's quite straightforward because the force and the displacement are in the same direction. And we get about 600 joules of work done. Now we were given the mass of the box, but you'll notice that it doesn't matter what the mass of the box was. All we needed to know was the force acting on the box and the displacement. Let's say now that Ms. Roseberry applies a vertical force of 40 newtons on the 10 kilogram box as it slides 15 meters across the frictionless surface. Find the work done on the box. Work will be 0 in this case. Why? Well, Ms. Roseberry is not increasing the speed of the box, and thus its mechanical energy is not increasing, nor is it decreasing. Forces applied at right angles to the motion don't count. So in this case, we have the displacement along the horizontal surface, and we have the force, which is, it says it's a vertical force. Doesn't say whether it's up or down. Let's say it's down. Here we have the force is perpendicular to the displacement, and so 0 work is done. So there's a little more to the story again. The only part of the force that counts towards the work done is the component of the force that's in the direction of motion or opposite to the direction of motion. If the force is opposite to the direction of the displacement, then the work done is negative. If the force is in the same direction as the displacement, then the work done is positive. You can see here that there's an angle of theta between the force and the displacement, and so we can use this formula. So work is equal to force times cosine of that angle theta times delta D. So what happens in the case we saw just a moment ago? If the force and the displacement are perpendicular to each other, theta must be 90 degrees, and cosine of 90 degrees is 0. So this formula shows us mathematically why the work done on the object is 0 when the force and the displacement are perpendicular to each other. Let's say that Ms. Roseberry now applies a force of magnitude 40 newtons at a 60-degree angle with the horizontal to push a 10-kilogram box 15 meters across a frictionless surface. Find the work done on the box. So here we've got our given values. Again, our unknown is the work done. We'll use our new formula where we have cosine of 60 degrees, and when we work that out we get about 300 joules. So that's less work than we had before, because now only part of the force, only one component of the force, is in the direction of the displacement for the object. Which means less energy is transferred to the box, which means the box won't accelerate as much. If there's a friction force, it will do negative work on the object, because as I said, if there's a component of force that's opposite to the direction of the displacement of the object, negative work is done. So that means that friction will reduce the total mechanical energy of the object. So Ms. Roseberry applies a horizontal force of magnitude 40 newtons to push the 10-kilogram box 15 meters across the surface. But now there's a frictional force of 10 newtons. Find the work done by friction on the box. It says work done by friction, which means we're going to ignore the work done by Ms. Roseberry's applied force for this part. We only want the friction force for this one. You'll notice that the angle in this case is 180 degrees, which tells us that the friction force is exactly opposite to the displacement of the object. So the angle between the displacement and the force is 180 degrees. And we get negative 150 joules. The negative tells us that energy is being taken away from the box. So to calculate the total work done on the box, we have to add the work done by Ms. Roseberry plus the work done by friction. And you'll notice that the friction, once again, is a negative as we add it. So we get 450 joules for the total work done on the box, which means the total change in its mechanical energy is positive 450 joules, which means it has gained 450 joules of mechanical energy. The work done by friction would have gone into creating heat and sound energy. So that's what happens, and that would be considered wasted energy, because we don't get that energy back. It's no longer useful to us. Power is the rate at which work is done on an object, or in other words, the rate at which energy is transferred to or from an object. We can calculate power with this formula, work divided by delta T, or delta E over delta T. Sometimes you'll see it written this way, change in energy over the time interval. The units for power are watts, named after James Watt, one of the scientists responsible for designing the first steam engine. And 1 watt is equivalent to a joule per second, which shows us that it's indeed the rate of energy transfer. One of the places where you would see watts would be a light bulb. This is an incandescent light bulb. We don't see those very often anymore, but the new compact fluorescent bulbs will also show you their power output. Typically they're around 10 or 11 watts for those new bulbs. The older bulbs used to be around 60 watts, but they could be up around 100 watts as well. So they used to have a much higher power output, which meant that we used a lot more energy when we used these bulbs. Alright, now you can do a little bit more practice using mechanical work and energy, and we'll see how we do.